welcome. You're probably here because you want to get a real handle on aircraft welding, quickly and without getting lost in the weeds.
Exactly. And that's what this deep dive is for. We're taking Chapter 5 on aircraft welding as our main source.
Right.
And the idea is to pull out the really key stuff, the most important info for you.
So our mission today, give you that solid foundation, understand aircraft welding, its history, how it's done, the gear, the safety, all that.
We'll cover the different methods in the source from, the older gas welding right up to the modern electric arc stuff.
Okay, sounds good. Let's dive in. Where did this all start, historically speaking?
Well, it might actually surprise you, but welding itself, the basic idea, goes way, way back, further back than planes.
Really? How far?
We're talking Bronze Age, believe it or not.
Wow.
But for aviation, the key thing is that some of the very first successful commercial aircraft, they actually used welded steel tube frames.
That is interesting. So they were welding steel right from the early days.
Right.
What changed then? Why move away from that?
It really comes down to that constant push in aircraft design, lighter materials.
Ah, okay. Weight savings.
Exactly. As the technology moved on, they started using more aluminum, magnesium, titanium, lighter stuff.
And steel welding techniques didn't work so well on those.
Well, these lighter metals, they just behave differently when you heat them. Different heat transfer, different metallurgy. So yeah, they needed new welding methods to handle them properly.
Okay, so let's get back to basics. What is welding, fundamentally? The source has a definition.
It does. Basically, it's joining metal pieces, usually by melting the edges together or sometimes by heating and hammering them until they fuse. It's a core process, really.
And is it super difficult to learn? For someone maybe listening who's curious.
That's a good point. The source actually suggests that, with the right tools and guidance and obviously practice.
Right.
Practice, someone with decent mechanical skills and good hand-eye coordination can definitely learn to weld. It's achievable.
Good to know. The source mentioned 3 general types.
Yep. Gas welding, electric arc welding, and electric resistance welding. Those are the main families.
Let's take gas welding first. It sounds kind of old school, but you said it was important early on.
It was foundational, yeah. The basic process uses a really high-temperature flame to melt the metal edges you want to join.
How hot are we talking?
The common one, oxyacetylene, hits about 6,300 degrees Fahrenheit. Really hot.
Whoa. And there's an alternative fuel mentioned, hydrogen.
Correct. Hydrogen can be used, especially for aluminum. But the flame's a bit cooler, maybe around 4,800 degrees.
So why was gas welding the go-to for early planes?
Well, think about the materials back then. It was the main way they joined metals thinner than, say, 316 of an inch, which covered a lot of aircraft structure up until the mid-1950s or so. It wasn't that it couldn't do the job later, but other methods became more efficient, economically speaking, for mass production.
But it's not totally gone, right? It's still used sometimes.
Yeah. Oh, definitely. It's still really useful for repair work.
Yeah.
Dependable. So if you're working on older aircraft or specific repairs, knowing gas welding is still valuable.
Okay. So the equipment for oxyacetylene, what's the basic kit look like?
Right. The source lists it out. You need the gas cylinders, obviously acetylene and oxygen. Then pressure regulators for each with gauges to control the pressure coming out.
Got it.
Hoses red for acetylene, green for oxygen. That's standard. They connect to the torch.
And the torch itself.
The torch has a mixing head inside, and you attach different tips depending on the heat you need. Plus, safety gear is essential. Welding goggles, proper shade.
Right, eye protection.
A spark lighter, never a match, or cigarette lighter. Maybe a special wrench for the acetylene tank. And always, always a fire extinguisher nearby.
Makes sense. Okay, let's switch gears to electric arc welding. The source says this is huge in aviation today.
Absolutely. It's a whole family of methods, really versatile.
Yeah.
Used in manufacturing, used in repair. You can weld pretty much any weldable aircraft metal with the right arc technique.
And the source breaks it down into 4 main types. Let's start with SMW shielded metal arc welding, or stick welding.
Yeah, stick welding, probably the most common type people might have seen. It's relatively simple equipment-wise.
How does it work?
You have a coated metal rod, the electrode, clamped in a holder. That's connected to a power source, low voltage, high current, AC or DC.
And you strike an arc.
Exactly. You touch the rod to the metal, pull back slightly, and you get this intense arc. Over 10,000 degrees Fahrenheit.
Wow.
That heat melts the base metal and the end of the electrode rod itself.
Okay, and the shielded part, that's the coating.
Right. As that flux coating on the rod burns in the arc, it releases a gas.
Ah, okay.
That gas shields the molten puddle from air oxygen, nitrogen, which would weaken the weld, and the melted flux also forms a protective slag layer on top as it cools.
Clever. And this was used historically in aircraft building, too.
Yeah, the source mentions manufacturers like Stinson used stick welding for their steel fuselage structures, 40-130 steel. But importantly, they often followed that up with heat treatment afterwards to normalize the metal.
Right. Okay, next up, GMAW, gas metal arc welding, or MIG welding. How is this an improvement?
Well, you could see MIG as a step up in efficiency, especially for production. Instead of a coated stick rod you replace, it uses a continuous wire electrode.
Fed automatically.
Yeah, fed through the torch. And instead of flux on the wire, you have a shielding gas argon, maybe helium, CO2, or a mix flowing out of the torch nozzle.
So, same job as the flux coating, basically, shielding the weld.
Exactly. Protecting it from the atmosphere. It typically uses DC power, low voltage, high current. Great for high-volume manufacturing, fast, consistent.
But maybe not always ideal for repairs. The source noted a downside.
Yeah, that's a key point. With MIG, sometimes it's tricky to be absolutely certain about the weld's internal quality without cutting it open, doing destructive testing, which you usually want to avoid in repair situations. So there's a bit of a trade-off there between speed and, let's say, ease of inspection sometimes.
Okay. Moving on to GTAL, gas tungsten arc welding, known as TIG. The source really highlights this one for aircraft maintenance.
TIG is fascinating. It offers really high precision and control. It's often the go-to for things like stainless steel, magnesium, and thicker aluminum in aircraft work.
Gas tungsten arc. So it uses a tungsten electrode.
Right. And the key difference here is the tungsten electrode is non-consumable. It doesn't melt into the weld like a stick rod or MIG wire.
Okay, so how do you add metal to the joint?
The tungsten electrode just creates the arc super hot, over 5,400 degrees F, that melts the base metal. Then you manually feed a separate filler rod into the molten puddle.
Kind of like with oxyacetylene welding.
Exactly like that.
Right.
And again, gas tungsten arc, you have an inert shielding gas, usually argon or helium, flowing around the electrode to keep oxygen out.
And TIG is quite versatile. The source mentioned power supply options.
Very versatile. You can use DC, direct current, for steels, stainless, titanium, or you switch to AC, alternating current, which is really important for aluminum and magnesium.
Why AC for aluminum?
The AC current helps break through the tough oxide layer that forms instantly on aluminum and magnesium. Makes it possible to get a clean weld.
Interesting. Okay, the last main electric arc method. Electric resistance welding. Spot and seam welding. Don't hear about these as much.
Probably because they're mainly used in manufacturing, joining thin sheet metal very efficiently. Factory stuff, mostly.
How does spot welding work then?
You clamp the metal sheets between two copper electrodes, apply pressure, then pass a strong electric current through.
Okay.
The metal resists the current more than the copper, so it heats up really fast right between the electrodes and melts locally. The pressure fuses those molten spots together. Zap, zap, zap.
And seam welding is just continuous spot welding.
Pretty much. Instead of fixed spot electrodes, you use rotating copper wheels. The metal passes between them, and you get timed pulses of current creating overlapping spots. Makes a continuous, often leak-tight seam.
Like for fuel tanks.
Exactly. Things like that.
Now, there's one more arc process mentioned. Plasma arc welding, PAW.
Yeah.
Sounds advanced.
Yeah. It is, relatively speaking, developed in the 60s specifically for better control over the arc. It offers really high precision, often used with automated setups for tiny or critical welds.
Well, I do it by hand.
You can, yeah. Requires similar skill to TIG welding. The torch is a bit different, though.
How so?
It has a non-consumable tungsten electrode, like TIG, but it's recessed inside a small nozzle. You start a pilot arc, then transfer a main arc to the workpiece.
What makes it plasma?
The key is forcing the arc, and a plasma gas, usually argon, through that very constricted nozzle opening. It creates this incredibly focused, super hot plasma stream.
Okay.
And there's usually a secondary shielding gas around that, too.
What are the big advantages? Why use plasma?
It can weld most metals over a wide range of thicknesses. The low heat input is great for really thin stuff, and for thicker materials, especially automated, it can do this keyhole technique.
Keyhole? What's that?
The intense plasma actually punches a hole right through the metal. As the torch moves, the molten metal flows in behind the hole and solidifies. Creates a deep, narrow weld, often in one pass.
That sounds impressive. Any downsides?
Well, doing it manually takes a lot of skill, like TIG, and the equipment is more complex and expensive, so you mostly see it in manufacturing or very specialized repair shops.
Okay, that covers the main welding processes. Let's talk about the gases involved. We keep mentioning them. Acetylene.
Right, acetylene. That's the main fuel gas for oxy-fuel welding and cutting. Key thing is, it's a bit unstable on its own.
How do they store it safely then?
It's dissolved in acetone within a special cylinder packed with porous material that keeps it stable, but you never want the working pressure for acetylene to go above 15 psi. Very important safety limit.
Got it. And argon and helium, the inert shielding gases.
Yep. Inert means they don't react easily. They just displace the air around the weld pool in MIG, TIG, and plasma, preventing oxidation. Argon's heavier, often gives good coverage. Helium can sometimes produce a hotter arc. Both are colorless, odorless, non-toxic.
What about hydrogen and oxygen?
Hydrogen is flammable, used sometimes for underwater cutting or in oxyhydrogen welding, particularly for aluminum, as we mentioned. Oxygen isn't flammable itself, but it's the oxidizer. It makes the fuel gas burn much, much hotter, hot enough to melt metal, essential for oxy-fuel processes.
Okay. And to handle these gases safely, you need regulators. What exactly do they do?
Regulators are crucial. They attach to the high-pressure cylinder and step that pressure down to a safe, usable working pressure for the torch.
They usually have 2 gauges, right?
Yeah, typically one shows the high pressure left in the tank, the other shows the lower working pressure you set with the adjustment knob.
And there are single-stage and 2-stage ones.
Right. Both do the same basic job, but a 2-stage regulator maintains a more constant outlet pressure, even as the cylinder pressure drops. They're usually a bit bigger.
Okay, gas regulators, then hoses. What's important about welding hoses?
Safety and compatibility. Usually they come as a bonded twin hose, red for fuel gas, acetylene, green for oxygen.
Left-hand threads for acetylene, right-hand for oxygen.
Correct. That prevents accidentally mixing them up. Hoses are marked with their size, pressure rating, maybe oil resistance. And critically, there's grade. Grade R is only for acetylene. T grade is needed for other fuel gases like propane.
Safety features check valves and flashback arresters. Tell us about those.
Absolutely essential. Check valves only allow gas to flow one way, preventing dangerous reverse flow.
Okay.
Flashback arresters are even more critical. They stop a flame from traveling back up the hose into the regulator or cylinder if something goes wrong. Catastrophic failure prevention. They usually include a check valve, plus a way to extinguish the flame.
Very important. And torches themselves, different types.
Yeah, the source mentions a few. Equal pressure torches are common for oxyacetylene, using both gases at similar low pressures. Injector torches use low-pressure fuel gas, and high-pressure oxygen creates suction. And cutting torches, often attachments, add that high-pressure oxygen jet for cutting.
And the torch tips seem vital.
Totally. The tip controls the gas flow and shapes the flame, which determines the heat applied. Using the right size tip for the metal thickness is key.
Too small, not enough heat, too big, too much heat, maybe burn through.
Exactly. Tips are numbered and manufacturers have charts. You match the tip to the job and set the regulator pressures accordingly. Keeping tips clean is also vital to prevent blockages and backfires.
Eye protection, non-negotiable, you said.
Absolutely. For oxy-fuel, you need goggles or a shield with the right shade lens to protect from the intense light and sparks. And it's different from the protection needed for arc welding, which is much brighter.
What about that yellow flare when welding aluminum with flux?
Ah, yes, a sodium flare. It's intensely bright. They developed special green lenses specifically to filter that out. Makes a huge difference in visibility and safety when welding aluminum. Meets safety standards too.
And lighting the torch only use a friction lighter.
Only a friction lighter or striker produces sparks safely. Never use matches, butane lighters. Way too risky. A gas buildup could ignite violently.
Okay. And filler rods for oxyacetylene. What's their role?
They add material to the joint to fill the gap, provide reinforcement, achieve the right strength, or maybe corrosion resistance.
Ferrous and non-ferrous.
Right. Iron-based or not, they come in standard lengths, different diameters. You pick the diameter based mainly on the thickness of the metal you're welding. Too thin a rod, maybe not enough fill. Too thick, can chill the puddle. And always use clean rods.
Okay, that's the gear covered pretty well. Let's walk through setting up the oxyacetylene equipment safely.
Right. Procedure matters here. First, always keep cylinders upright and secured, especially acetylene.
Because of the acetone.
Exactly. Crack the cylinder valve quickly before attaching the regulator blows out any dust. Connect regulators, left-hand thread for acetylene, right for oxygen. Make sure the adjusting screws are backed out.
Hoses next. Red to acetylene, green to oxygen.
Correct. And this is where you'd install flashback arresters, ideally right at the regulator outlets. Then stand to the side, open the cylinder valve slowly, oxygen fully open, acetylene maybe just 1.5 turns. Don't let cylinder pressure get too low, say below 20 psi.
Purge the hoses before connecting to the torch.
Yes, in a well-ventilated area, away from sparks. Just a quick burst of gas through each hose, then connect hoses securely to the torch inlets.
And leak checks. Absolutely critical.
Critical. Pressurize the system slightly, close the regulators, watch the gauges. If pressure drops, you've got a leak. Tighten connections. If it persists, use soaky water on all connections.
Wow.
Bubbles indicate a leak.
Never use a flame to check for leaks.
Absolutely never. Extremely dangerous.
We talked about tip size being important.
Crucial. Match the tip number to the metal thickness using the manufacturer's chart. Set the working pressures on the regulators according to that chart too. Using the wrong pressures for a tip can cause overheating, flashbacks, and make sure hoses aren't too long or kinked, restricting flow. Remember that acetylene withdrawal limit too.
Okay, system set up, leak checked. How do you actually light the torch and get the right flame?
Right. Well-ventilated area. Point the torch away from you. Open the torch's acetylene valve slightly, maybe a quarter turn. Immediately use the striker to light the gas.
You'll get a smoky yellow flame.
Yeah, adjust the acetylene valve until the black soot disappears, long yellowy flame. Then slowly open the torch's oxygen valve.
The flame changes color.
It gets shorter, turns bluish-white. You'll see a bright inner cone form. That's your neutral flame, the starting point.
And you adjust from there for different flames, carburizing, oxidizing.
Exactly. The neutral flame has a balanced mix, around 5,850 degrees F at the inner cone tip. Good for most steel welding.
Pulverizing.
More acetylene than oxygen. Slightly cooler. Has a greenish feather beyond the inner cone. Used for high-carbon steels, sometimes aluminum.
Unoxidizing.
More oxygen. Hottest flame, about 6,300 degrees of F. Short outer flame, pointy, purplish inner cone. Used for things like bronze welding, but can burn steel. You can also adjust pressures for a softer or harsher flame, but always stay under 15 psi for acetylene. Softer flame is often better for aluminum.
The source warned about backfires and flashbacks, too. What are they?
A backfire is like a pop at the tip, flame goes out, caused by touching the work, overheating, wrong pressure, dirty tip, usually just annoying.
Flashback sounds worse.
Much worse. That's when the flame burns inside the torch or hoses, makes a loud hiss or squeal, caused by bad connections, wrong pressures, overheating.
What do you do if that happens?
Immediately shut off the gas at the cylinders. Acetylene first, then oxygen. Find and fix the cause before relighting. Flashback arresters are your main safety net against this reaching the cylinders.
Okay, briefly, oxyacetylene cutting, different from welding.
Yeah, cutting steel is basically rapid, controlled burning or oxidation. You use a cutting torch attachment.
How does it work?
You preheat the steel to bright red with smaller flames on the cutting tip, then hit a lever that releases a high-pressure jet of pure oxygen.
And the oxygen does the cutting.
It reacts with the hot steel, forms molten slag, and the oxygen jet blows it away. Move the torch steadily, and you cut through. Fast way to cut steel, though not super precise.
And shut down. Just as important as setup. Correct sequence.
Absolutely. First, turn off the flame, close the torch acetylene valve, then the torch oxygen valve. If done for the day, close the main cylinder valves tightly.
Then relieve pressure in the hoses.
Yes. Open each torch valve one at a time in ventilated area until gauges read 0. Close torch valves, then back out the regulator, adjusting screws completely until loose. Coil hoses carefully, store everything safely.
Okay, let's get into the doing it part. Oxyacetylene welding techniques. Hand positions, angles.
Details matter. For thin stuff, maybe drape hoses over your wrist for better torch control. Heavier stuff, a firmer grip. Angle the torch tip 30 to 60 degrees to the surface, pointing slightly forward to preheat.
More vertical for thicker metal.
Generally, yeah, helps penetration. Keep the tip of that bright inner cone about 18 inch off the metal.
And moving the torch forehand versus backhand.
Forehand is more common for layer materials. Flame points in the direction you're moving. Filler rod is ahead of the torch.
Backhand.
Flame points back towards the finished weld. Rod goes between flame and puddle. More heat concentration, sometimes used for thicker metal, but less common in aircraft work.
Forming that molten puddle is key, right?
Yes. Get the heat right. A small puddle forms along the joint line, melting both pieces. Move the torch in little circles or semicircles, keeping heat even. As it melts, dip the filler rod into the leading edge of the puddle to add material.
Rod diameter related to metal thickness.
Usually about 1/4 of the base metal thickness.
Yeah.
And make sure the rod material matches the base metal.
What does a good weld look like afterwards?
Smooth, consistent bead, even ripples, uniform thickness, slightly rounded top, convex. Edges should blend smoothly into the base metal, no undercut or overlap.
What about problems?
Look out for blowholes, porosity, little gas bubbles, unmelted filler blobs. The metal next to the weld shouldn't look burnt, pitted, or cracked. A clean look is good, but strength is key. Never file a weld to make it look better that weakens it. If it's bad, grind it all out and start over.
Okay. Welding-specific metals now? Ferrous metal steels.
Low-carbon steel, 4130. Cast steel generally weldable with oxyacetylene. Use a neutral flame for most. Maybe slightly carburizing for high-nickel chromium stainless steels. Soft flame, control the puddle, keep the rod tip shielded by the outer flame. Let it cool slowly afterwards, heat gently to dull red, then pull torch away slowly. Helps prevent brittleness.
What about 4130 chromoly specifically? Common in airframes.
Similar technique to basic steel, but for thicker sections, say over 316-inch, preheating is often vital. Heat the area around the joint to 300-400 F first.
Why preheat?
It slows the cooling after welding, prevents forming brittle martensite, which can cause cracking. Use a soft, neutral flame. Oxidizing flame bad, carburizing flame also bad, increases hardenability. Use the right 4130 filler rod. For critical structural welds, post-weld heat treatment is often required. TIG might be better for thick 4130, but still needs heat treatment.
Stainless steel with oxyacetylene. Any tricks?
Generally only for non-structural stainless. Welding can reduce strength and corrosion resistance in structural types. Use a slightly carburizing flame, helps prevent chromium oxides, but don't overdo it. Maybe a slightly smaller tip than for steel.
Need flux for stainless?
Absolutely. Special stainless steel flux. Apply to underside and the rod. Keep rod in the flame envelope. Avoid stirring the puddle. Don't re-weld over stainless welds. TIG is often preferred for stainless, no flux needed.
Okay, non-ferrous now. Aluminum, big one for aircraft.
Gas welding aluminum takes practice. It melts suddenly with little warning. Practice on scrap first. Slight torch angle is better, usually for thicknesses between 0.031 and 0.125 inches. Alloys like 1100, 3003, 5052 are weldable. Heat-treatable ones like 6061 need reheat treatment after welding.
Cleaning is critical for aluminum.
Absolutely paramount. Solvent clean first, then stainless steel brush right before welding to remove the oxide layer. Use a tip maybe one size larger than for steel. Set pressures carefully. Use those special green goggles for the flux flare.
And you need aluminum flux.
Yes. Mix to a paste, apply to joint and rod. Tack weld first, maybe skip the first inch, weld the rest, come back to the start. Ease off heat at the end, dabbing motion with the rod. Crucially, clean all flux off immediately afterwards with hot water and a brush. It's corrosive. Prime and seal promptly.
Magnesium similar to aluminum.
Similar equipment, yes. But magnesium expands even more with heat, so joint fit up and avoiding stress is even more critical. Don't use rigid fixtures. Use matching filler rod. Never weld magnesium to aluminum.
Need flux for magnesium too.
Yes, special magnesium flux paste. Use sparingly. Same eye protection helps. Neutral flame. Similar tip size to aluminum. Similar technique. Again, TIG has often replaced gas welding for magnesium because the flux is corrosive and TIG offers more control.
Okay, that covers gas welding variations.
Yeah.
The source then talks about brazing and soldering lower temperature joining. Steel brazing first.
Right. Brazing uses a filler metal that melts above 800 F, but below the melting point of the base metals. The base metals don't melt.
So the filler flows in by capillary action.
Exactly. Bonds through molecular attraction. Less heat than welding can join to similar metals. But the joint isn't as strong as a weld, not for critical structures or high temps.
Preparation.
Bevel edges sometimes. Parts must fit closely for capillary action. Need brazing flux, cleans oxides, helps filler flow, can be on a rod or applied separately.
Heating process.
Heat the base metal slowly, evenly with a neutral flame until it's hot enough to melt the filler when touched. Don't melt the filler with the torch directly. Add filler rhythmically. Watch the flux, its appearance tells you about the heat. Filler flows towards heat. Clean all flux off afterwards, hot water, brush.
Can you braze aluminum too?
Yes, with an aluminum silicon filler that melts slightly lower than the base aluminum. Needs special aluminum brazing flux. Good for lap joints, attaching fittings. Use acetylene or hydrogen, same eye protection helps. Use a slightly reducing flame, maybe smaller tip, heat with outer flame. When flux is clear liquid, apply filler. Clean flux off thoroughly afterwards. Works best on alloys like 1100, 3003, 6061.
And soldering even lower temperature.
Right. Filler melts below 800F. Again, capillary action into close-fitting joints. Soft solder, tin lead alloys, used for copper, brass seals, electrical connections. Doesn't need an oxy-fuel torch, propane torch, or soldering iron works.
Still need flux.
Yes, cleans, helps flow. Most fluxes need cleaning off after. Rosin core solder is used for electronics. Rosin isn't corrosive.
Can you solder aluminum?
Yes, with special aluminum solders and fluxes. Can use a soft oxy-fuel flame or propane. Similar prep to brazing. Lap joints best. Clean, flux, heat evenly, apply solder. Used for things like heat exchanger repair, not structural replacement for welding brazing.
What about silver soldering? Sounds stronger.
It is, often called silver brazing, used for high-pressure oxygen lines, parts needing vibration heat resistance, stronger than typical brazing. Joins copper, nickel alloys, steel, needs flux, cleanliness is vital. Lap, flanged, edge joints common. Use a soft, neutral, or slightly reducing oxyacetylene flame. Keep flame moving, preheat evenly. Apply solder when flux flows, clean afterwards.
Great overview of those processes. Let's swing back to TIG welding now and get into specifics for different aircraft materials.
Okay, TIG. Modern machines are pretty sophisticated AC/DC, pulsed, inverter tech, but the basic torch design is similar. Manipulating it feels a bit like oxy-fuel, but heat is controlled electronically, often with a foot pedal.
Tungsten electrodes, different types.
Yeah, thoriated, zirconiated, often for DC. Pure tungsten, often for AC on aluminum magnesium. Follow the machine manufacturer's advice. Shape the tip properly on a dedicated grinder. Pointed gives wider arc. Blunter gives deeper penetration. Manual has guidance. Standard weld quality rules apply.
TIG welding, 4130, steel tubing, common stuff. Specifics.
Basic technique similar to other steels if thin, under 0.120 inch. Cleaning is very important. TIG is sensitive to porosity, hydrogen embrittlement. Use high-frequency start if possible. Avoids touching electrode to work. Avoid drafts.
Preheating 4130 for TIG.
Generally not needed for thin wall. But post-weld tempering, stress relief, is highly recommended. TIG cools fast, can cause brittleness. Heat the whole weldment evenly to 1100, 1200 F dull red after it cools. Hold briefly, let cool slowly.
Right.
If using 4130 filler, preheat and post-heat are even more critical to avoid cracking. Always consult engineering specs for critical parts.
Stainless steel via TIG. Differences.
Usually 300 series stainless is readily TIG weldable. Lower melting point, lower thermal conductivity than steel, so use less current. But higher thermal expansion, prone to warping.
How do you manage the warping?
Use skip welding, backstep welding, fixtures, more tack welds. Choose a compatible filler rod, 309, 36 ton, 347, etc. Clean thoroughly just before welding. Use forehand technique, steady speed. Dip rod into leading edge of puddle. Shielding both sides, back purging, is ideal, especially for tubes. Or use backing flux underneath, good for exhaust repairs.
TIG welding aluminum, very common, you said.
Yeah. Technique is a bit like oxy-fuel, but use AC power. The AC cleans off that tough oxide layer. Argon is usually the preferred shielding gas for manual TIG on aluminum, better coverage. Cleaning. No flux needed with TIG.
Okay.
Clean thoroughly, base metal, and filler rod. Back purging helps for tanks, gives smooth inside bead. Similar torch rod angles to oxy-fuel. Keep arc short. Don't touch electrode to puddle, contaminates tungsten. If you do, stop, regrind the tip.
And magnesium alloys with TIG?
Similar joint prep. But high thermal conductivity and expansion mean fixtures are often needed to control stress and cracking. Use smaller beads, faster speeds, maybe lower melting filler rods. Can use DC or AC with high frequency. DC reverse polarity gives good cleaning, often used manually. Argon is common shielding gas. Use zirconiated, thoriated, or pure tungsten electrodes. Short arc length, frequent tacks. Weld from middle outwards. Minimize stops. Aim for single pass.
TIG welding titanium. Sounds like it needs extreme care.
Utmost care. Cleanliness and shielding are everything. Ideally, weld in a clean room, controlled humidity, no drafts. Use DC straight polarity, water-cooled torch, large gas cup, maybe gas lens for smooth flow. Thoriated tungsten recommended.
Shielding is critical.
Absolutely. Molten titanium reacts with everything, oxygen, nitrogen, hydrogen. Need perfect shielding on top, on the trailing edge as it cools, and underneath, root side. Use trailing shields, backup shields, copper bars, purge tents. Meticulous cleaning detergent or non-chlorinated solvent like alcohol. Clean gloves, too. The weld color tells you the quality. Bright, shiny silver is perfect. Strong color, okay. Dark blue or white powder means bad contamination. Grind out and redo with better shielding.
That's incredibly detailed on TIG. Let's briefly cover some essentials for stick welding, SMAW. beyond what we first discussed.
Okay, stick welding. Ensure good ground connection first. Clamp electrodes securely. Wear all the PPE helmet, gloves, leathers, boots. Respirator if needed. Check ground, electrode type size, polarity setting, current setting.
Striking the arc needs practice.
Definitely. Touch electrode to metal, lift slightly, 18 to 14 inch to establish arc. If it sticks, quick twist usually frees it. If not, shut off machine, carefully chip it off. 2 methods. Tapping, vertical tap, lift, or scratching, low angle sweep, lift. Needs speed and coordination.
Creating a uniform bead.
Move electrode smoothly along joint, steady speed. Feed electrode down as it melts. Too slow, wide, irregular bead. Too fast, narrow, poor fusion. Listen for the arc. Sharp crackle is usually good. Good bead is uniform, slight reinforcement, good tie-in at edges, minimal spatter, proper penetration. Maintain consistent electrode angle, 20 to 25 degrees.
Restarting a bead if you stop.
Chip all slag off the crater first. Start arc just ahead of crater, move back to fuse, then continue forward. Essential to remove slag to prevent inclusions.
Multiple passes for thick metal.
Yes. Layer beads in sequence, clean slag meticulously between every pass. Thicker plates often need edges beveled into a groove, then fill the groove with multiple beads.
Welding in different positions must be harder. Vertical, overhead.
Much harder. Need to adjust current, maybe electrode type, arc length, technique. Gravity works against you. Vertical often needs lower current. Upward vertical, maybe focus arc on sides. Downward vertical, maybe tilt electrode up slightly, move faster.
Overhead sounds toughest.
It is. Need very short arc length to control the puddle, stop it dripping. Full PPE is non-negotiable. Keep head to the side. Consistent motion is key. If metal sags, briefly whip electrode away to let it cool slightly, then return.
Okay, one last major topic. Managing metal expansion and contraction during welding. Huge issue, right?
Fundamental issue. Metal expands when heated, contracts when cooled. Uneven heating cooling means uneven expansion contraction, which creates internal stress, can cause warping, buckling.
Coefficient of linear expansion.
That's the material property, how much it expands per degree temperature change. Total change depends on that, the temperature difference and the original size. Thin sheet metal warps easily because heat spreads and cools quickly, creating big temperature differences.
How do you control it? Chill bars.
Yes, chill bars, heavy copper or steel pieces near the weld act as heat sinks, pull heat away faster, reduce the temperature spread. Fixtures can do this too.
Tack welding helps.
Definitely. Small welds along the joint hold things in alignment, control overall movement. For long seams, metal might pull together as it cools, so sometimes you start with a wider gap at one end.
Preheating.
Very effective, especially for tubes, castings, complex joints. Heat the whole part somewhat uniformly before welding. Allows more even expansion during welding and more even contraction afterwards. Reduces stress buildup.
Okay. The source shows common joint types for oxyacetylene. Butt joints.
Edges together. Plain butt for thin metal. Flanged butt for very thin, edges bent up. Beveled butt for thicker metal, V-groove, etc., to allow full penetration. Needs filler.
T-joints.
One piece joined to the surface of another at 90 degrees. Common in tube frames. Plain T usually okay. May need beveling for thick parts or root gap for penetration.
Edge joints. Corner joints. Lap joints.
Edge joints join bent-up edges, often for non-structural sheet metal. Corner joints form a corner, may need filler reinforcement. Lap joints overlap pieces, not ideal for strength with oxyacetylene, but common for spot welding.
Specific repairs for steel tubing now. Dents at a cluster weld.
Can use a formed steel patch plate. Same material, same or thicker gauge. Weld over the dent, extending onto adjacent tubes. Form it to fit snugly first. Weld all edges.
Dents between clusters.
Straighten dent if possible. Stop drill any cracks. Use a welded split sleeve reinforcement. Sleeve of same material thickness. Inside diameter matches outside of tube. Cut sleeve diagonally at ends, split lengthwise. Clamp over dent, weld seams and ends.
Splicing tubes. Inner sleeve method.
Cut out damaged section, diagonal cuts. Cut replacement section slightly longer. Use 2 inner sleeves. OD matches original tube ID. Align parts, tack with rosette welds. Weld inner sleeves to original tube through gaps at ends.
Outer split sleeve splicing.
Use perpendicular cuts on original tube. Replacement tube matches length exactly. Use 2 outer sleeves, same material thickness. Cut with fish mouth ends, 30-degree V. Slip sleeves over replacement, slide over joints, tack, then weld sleeve ends. Hold one sleeve, let cool, weld other.
Okay, nearly there. Landing gear and engine mount repairs. Saturn rules.
Some steel tube axle assemblies can be welded, but if originally heat-treated, they must be heat-treated again after repair. Critically important.
What's generally non-repairable by welding?
Often, heat-treated landing gear struts with machined surfaces, like oleos, spring steel gear legs. Welding ruins the properties and tolerances. Streamlined tubing, sometimes repairable with inserts, round or streamlined.
Engine mounts. High stress area.
Needs experienced welders. Vibration is intense. Preferred repair often involves telescoping a larger tube over the stub using fishmouth and rosette welds. Maintaining alignment is critical. Use a fixture or bolt mount to engineer frame during welding.
Wow. That covers an incredible amount of ground on aircraft welding. It's complex, but that chapter gives a really solid base.
I think so too. You've got the history, the methods from gas to TIG to plasma, the equipment, materials, and the vital safety aspects, a good handle on the fundamentals.
So for anyone listening who wanted that quick but thorough understanding, you should feel much more informed now. Definitely a strong starting point if you want to dig deeper into any specific area.
Which does make you wonder, considering how materials and techniques keep evolving, what do you think the next big innovation in joining methods for aerospace might be? Something to ponder.
That is a great question to think about. Well, thanks for joining us on this deep dive into the world of aircraft welding.